Hi, so today we're going to be looking at simple harmonic motion and we'll be doing some past paper questions on that. Okay, so we'll start off by looking at some questions from paper 1 and let's go about it. So the graph shows how the velocity v of an object undergoing simple harmonic motion varies with time t for one complete period of the oscillation. Okay. And so they want us to find how the total energy E of an object is going to change. Okay, so when it comes to these simple harmonic motion questions, it's always good to visualize a simple pendulum. Okay, now you have to realize that for a simple pendulum, it's not a perfect representation of simple harmonic motion, but it's a good approximation, and intuitively it's easier to understand. Okay. So right here we have a simple pendulum, and what we see is that at this position you have your equilibrium. Okay. At the position to the right you have your maximum amplitude. Okay. So this is your maximum amplitude, and at the position to the left you have your minimum amplitude. Okay, because you're going to the left. So basically over here, what you can see is that at the equilibrium position, the displacement x is 0. Okay, the displacement x is 0. The acceleration a is also 0. Okay, so at the equilibrium position, we will say that the acceleration is 0 and the velocity v is the maximum. So this is the absolute value of the velocity. So we're talking about the magnitude only. So you have a maximum magnitude at the equilibrium position. Okay. Now, in this case, when we go to the amplitudes over here, also one thing you have to realize is for a simple pendulum, what we can see is that the net force, if you have a tilted axis, which we have over here, in a pendulum, we're going to be looking at a tilted axis. So we have looked at this in the videos where this axis, moves with the pendulum bob. And so the axis keeps changing like this. Okay. Oh, and actually, in this case, this should be negative x. Okay, so the reason that side is negative x is because you're going to the left. And so you get this axis movement that's going on in a given pendulum, right? So this is how the pendulum works. So we have seen that the net force acting on the pendulum, it's basically given by this formula. So this formula is negative g sine of theta. Okay. So over here, the force is negative because you're going in the negative x direction. Okay. And similarly, when you get to this point, the force is given by negative g sine of theta. But because you go the opposite direction, this becomes negative g sine of negative theta. And in this case, sine of negative theta is negative sine theta. So the negative and negative cancels out. And this just becomes g sine theta in the positive direction because you're going in the positive x direction. Okay. So the main thing we get from this is that the net force in a simple pendulum motion comes from this value of g sine theta, right? Which we have calculated in our concept videos. And so when you reach the equilibrium position, the acceleration just becomes some value of negative g sine of theta. But at the equilibrium position, theta is 0. So this is negative g sine of 0. And we know that sine of 0 is equal to 0. So therefore, the acceleration becomes 0 meter per second squared. Okay. So because of that, at the equilibrium position, the acceleration is 0. So the displacement is 0, acceleration is 0, and the velocity is at the maximum. And the reason the velocity is at the maximum at the equilibrium is because when you go to the amplitudes, you get a maximum height. So you have maximum gravitational potential energy. And then as the ball starts to move downwards, all that gravitational potential energy just gets converted to kinetic energy. So if the kinetic energy is rising, then the velocity rises, and that's precisely why you have a maximum magnitude of the velocity at your equilibrium position. Okay, so we have looked at the equilibrium position. So these are just pointers to remember. Okay, now when you go to the amplitude, you find that on the left amplitude you have minimum displacement, right? This is your left amplitude, so I'll call this negative A. The displacement is the minimum because you're at most to the left position. The velocity becomes 0 at the amplitude, right? So if you can think of this as a construction ball, for example, then if you release the construction ball over here, it's going to have a high velocity. And then as it goes back over here, you're going to reach the point of minimum velocity. Okay? So this is actually like max height, right? And that's where the minimum velocity will happen. So if you want to look at it in terms of intuition, then you can think of it in terms of projectile motion. So we know that in projectile motion, this is the function of height over displacement, or this is like y over x. And we see that when you reach your maximum height, so this is your max height, we see that when we reach the maximum height, the velocity in the y direction just turns to be 0 meter per second. Okay, so that's sort of similar ways of thinking why the velocity is 0 at the max height. Okay, the other thing is that the acceleration is actually the maximum at this point. Okay, so the reason the acceleration is maximum is because the acceleration is negative g sine of theta. But because this is theta is negative, this is negative g sine of negative theta, which just becomes positive g sine theta. And as we can see, the acceleration is acting in the positive x direction, so it's positive, right? And because of that, it becomes positive g sine of theta. Okay? So the value of x is minimum, the velocity becomes 0, and the acceleration is at the maximum. And if you move on to the left amplitude, what you will see over here is that the value of x is at the maximum. So this is the maximum value of x, right? The velocity is once again 0, and the acceleration becomes the minimum. Okay? The reason acceleration becomes minimum is because the acceleration is negative g sine of theta, and because theta is positive, the acceleration just stays negative. So you have the minimum value of the acceleration. And because this acceleration is acting to the left, that's why it has a negative value. Okay? So therefore, at your maximum amplitude, the velocity is once again 0, the displacement is maximum, and the acceleration is minimum. Okay? And one thing to see over here is that we know that acceleration is proportional to negative x. So if acceleration is very high, we know the displacement will be very low. And if the acceleration is very low, we know the displacement will be very high, right? So if acceleration is minimum, x is maximum, or displacement is maximum. If acceleration is maximum over here, right? If acceleration is maximum, then displacement is minimum, okay? So you get this sort of inverse relationship. Okay. So with all of those things listed down, we can sort of visualize how to do these questions. Okay. So we look at this graph over here, which shows how the velocity v of an object varies with time. Right. So the way we can go about it is that once again we draw a simple pendulum over here. So this is going to be our simple pendulum. Okay. And what we can see is that the velocity is 0. It's starting off at 0. And so immediately we can say that we are at one of the amplitudes. Okay. Because the velocity is 0 at the amplitude, as we can see over here. So the velocity is 0 at the amplitude. Okay. So now what's happening is that the velocity is falling, and then it reaches the negative velocity, and then it goes back to 0. So we can actually color code it. So this is the first section. So we can see that the velocity starts at the positive x direction, and it's 0. Then it goes towards the equilibrium. And as we have seen, the absolute value of the velocity is maximum at the equilibrium. So this is the maximum velocity in absolute terms. Okay. So because we reach this point, we know that this red section corresponds to this section. Okay. Now, once we have done that, we can go to the other section. And one thing you have to realize, it happens for one complete period of the oscillation. Okay. So we're going to show one complete period of this pendulum motion where the starting and the ending point is the same. Okay. Now in the second point, this is your second movement. So the pendulum goes from equilibrium to your negative amplitude, and so you get this position. And once again, we know that at the amplitude the velocity is 0, so that's how it will function. Now once the pendulum goes to the negative amplitude, it comes back again, and as we can see, because the pendulum is going to the right, the velocity is positive. Okay, so because the velocity is positive as it's going to the right, the velocity is rising, it goes in this purple direction towards here. And like we said, once it's at the pendulum, at your pendulum, the absolute value of the velocity is the highest, so that's why you have your max velocity. Okay. And to complete the period of the oscillation, the pendulum goes back from the equilibrium to the maximum amplitude. And so you get this motion. And we see once again that at your maximum amplitude, the velocity is 0. Okay. So this this is a color-coded way of showing exactly how we can visualize this graph on our, how we can visualize this graph on a simple pendulum. Okay. Now after this, they're asking us, how does the energy E vary for an object with time t, right? So as we have seen over here, we can see that in this case, for any pendulum, let's say that, if this is the negative amplitude, and then let's say that if this is the positive amplitude and this is the equilibrium, then this purple graph, or this purple section over here, is basically just going to show you the graph for gravitational potential energy. And then this green graph over here is going to show you the variation of the kinetic energy. So the kinetic energy is 0 at the amplitudes. And the reason is because, like we said, when we go to the amplitudes, the velocity is 0. And because the kinetic energy is 1/2 mv squared, then at the amplitude, the kinetic energy must be 0. So that's why the velocity, the kinetic energy becomes 0 at the amplitudes, and it is maximum at the equilibrium because the kinetic energy is maximum at the equilibrium. So this is a graph which you would have seen before. And so the kinetic energy and the potential energy, in this case, are complementary to each other. Okay, and the graph, if you look at the x and y axes for the graph, then on the y axis you've got energy, and then on the x axis you just have displacement. Okay, now the total energy in a simple harmonic motion based system, the total energy is just mgh. The total energy is just your kinetic energy plus potential energy. Okay. So in a simple pendulum, the potential energy is mgh, which is gravitational potential energy. But if you have a mass spring system, then the potential energy can also would also come from your 1/2 kx squared, which is elastic potential energy. So k is the spring constant, right? But basically the point is that the total energy is the kinetic energy plus the potential energy. And so if you want to find the total energy at, let's say, this value of the displacement, then all you do is that you take the potential energy at that point, you take the kinetic energy at that point, So let's say that if this is A, and then let's say that this is B, then the total energy is just A plus B. And if you do this for, some distinct set of points, if you do it for like many points like this, right, what you will see is that if you add it all up, then ultimately you're going to get this red line. So maybe you can draw this a bit higher. Yeah. So what this basically shows is that in a simple harmonic motion, the total energy, which is TE, this is total energy, will always stay constant. Okay? And this relates to the law of conservation of energy, that energy can neither be created nor be destroyed, but only be transformed from one form to another. So the total energy stays constant, and so that's why the clear answer for this is C. Okay? Because if you look at graph C, the total energy. So see over here, the thing is you need to read the question. So in the question they're saying that in this case you want to find total energy. Not the kinetic energy, not the potential energy, total energy. Which is why you get this straight line. So this is total energy. Okay? Good. So this was this is most of the basics that we need for this, right? And just remember these regions over here, okay? All right, so this is our first question. Now let's move on to our second question. So in the second question, the graph shows how the displacement varies with time t for an object that is undergoing simple harmonic motion. Okay? So when you see, then this is how the displacement changes over time. So which graph shows the object's acceleration a as it varies with time t? Okay. So the way you can think about it for this is that you can look at it in terms of you can see it through either the mathematical way or you can visualize it, right? So let's just see how to go about this. Okay, so we can start off first with the visualizing way, okay? So we have our simple pendulum over here. This is our simple pendulum. We draw different positions in the simple pendulum, like this, okay? So this is the simple pendulum, and these are the different positions as we have seen so far. Now, as we can see, this angle over here is theta, and this angle over here is negative theta. Now, in this case, the displacement over here is 0, okay? So we know that at the equilibrium, the value of x is 0. We know that at the positive amplitude, you have the maximum displacement, and then at the negative amplitude, you have the negative displacement. So this is like x min. Okay, so because the displacement starts off at 0, we know that we're going to be starting at the equilibrium because that's where displacement is 0. And then the displacement falls like this. So because it's falling, we know that we're going from 0 to negative min. Okay, so that's why you will go from 0 to negative min, because you're reaching the minimum displacement. So we know that this is min x, minimum displacement according to the graph. And then this is max x. Okay. Now, after you go to the minimum displacement, you come back. So as you come back, this shows this region over here. Okay. So the displacement is going from x min all the way to 0 again. So the displacement rises in this purple section. And then after the purple section, once again, you go from the equilibrium to the maximum displacement. So that's what it shows over here. Okay, you're going from equilibrium to maximum displacement. And as you can see, because the pendulum is going in the positive x direction, the displacement is rising. Okay, so always remember this Cartesian plane axis when doing physics questions, right? You need to be very sure about like directions and things like that. Now, after that, after the pendulum reaches the maximum height, it's going back to 0. and so it comes over here. It's back at 0. Okay, and as you can see, because the pendulum is going in the negative x direction, it's going on the left. That's why the displacement falls and the displacement goes back to 0. Okay, so this is one entire oscillation. As you can see, the pendulum bob ended up moving in this direction. So this is one oscillation because the starting point and the ending point is 0. So you start here, you go to the left, then you go all the way to the right, then you go back to 0. So that is one entire oscillation of this pendulum, and we saw the color-coded version of it. Okay, now we want to see which graph shows the object's acceleration with time t. So as we have seen, the object, is going to start. So we know that the object is going to start off at the equilibrium. That's how the motion is happening, right? So because you start off at equilibrium, we have seen that when we go to the equilibrium, the acceleration is 0. Okay, and the reason is because in this free body diagram, the acceleration in the x direction comes out to be negative g sine of theta, and at the equilibrium, theta is just 0 because it's a straight line. There's no theta. So this is negative g sine of 0 at the equilibrium, and so this just becomes 0. Okay, so we know that it's going to the starting acceleration is 0. Then the pendulum goes to the left, and we know that at the left amplitude you have maximum acceleration. Okay, and the reason is because once again the acceleration is negative g sine of theta, and in this case, when you go to this minimum amplitude, right, then the acceleration in the x direction is negative g sine of negative theta, and this just becomes g sine of theta because sine of negative theta is negative sine theta. So therefore, at the negative amplitude, you have max acceleration. Okay, so you go from 0 acceleration to maximum acceleration, right? And if you look at which graphs show this, well, the first graph does not show it because you have to start at acceleration as 0. The second graph does not show it because the acceleration is not at 0. So you have two choices between C and D, right? So you're starting off at 0 and then you're going down. But in this case, the acceleration is falling, right? And that cannot be the case, okay? Because as we have seen, when it goes to the left, you go to the maximum acceleration, and therefore graph D works the best, okay? So that's one way to look at it. The other way is the mathematical way. So you can just look at it in terms of sine functions and differentiation. If you have not done differentiation, then you will learn it in the next month or so, most likely, and it's not really that hard, right? Differentiation is just an elaborate way of finding gradients, okay? And once you understand the basis of it, it seems like any other chapter. So basically, in this case, you have displacement versus time, and you get this function over here, right? Now, what you can see is that, you have to train yourself for this, but this function will represent negative sine of theta, okay? So if we see over here, if we look at sine of theta versus theta, then we know that sine of theta oscillates from positive 1 to negative 1, and then this is how the oscillation is going to be, okay? So it's going to be positive 1 at 90 degrees, then at 180 degrees it's going to be 0, at 270 degrees it will be negative 1, and then at 360 degrees it will be 0, okay? So if you graph a sine curve, then a sine curve will sort of follow this pattern. Okay, so this is what sine of theta is going to look like. Okay, but what we have seen is, let's say if we graph a function, right? Let's say if this function over here, or actually let's draw, let's see. So let's draw this function as this function, okay? So let's say that this is 5. So we know that f of x is equal to 5. So if someone asks you to graph negative f of x, you'll just graph -5, which is this line, correct? So in this case, all you have done is you have taken this function f of x and then you have reflected it over the x-axis like a mirror. Okay? So in this case, we are going to be using this concept to recognize the graph. All right? And we can also look at another example to just show the reflection. And I would recommend that, for these functions, you can sort of experiment on Desmos, right? So what we see is that this function, let's say if you have this function, okay? Let's say if you have this function over here, right? So this function is going to show that y is equal to x squared. Then let's say that if this is y is equal to f of x, then negative f of x is just going to be reflected on the x-axis. So if this function is x squared, then this function becomes negative x squared. Okay. So if you want to graph negative f of x, you just reflect it on the x-axis. So in this case, if this purple line is sine of theta, then if you reflect the purple line along sine of theta, then you get this green line. Okay. So if the purple line is y is equal to f of x, then the green line is negative f of x. So we saw that the purple line is sine of theta, then the green line is going to be negative sine of theta. Okay? So by sort of visualizing it mathematically, what we have come to the conclusion that this function shows us negative sine of theta. And that's the displacement function. And after this, all we say is that the velocity is just your change in displacement by change in time. So this is just d by dt of negative sine of t. So you take the derivative of the displacement function. And if you take the derivative of the displacement function, you get negative cosine of t. So once again, this does not look as complicated. You'll learn it in differentiation if you haven't learned it already. Okay. And then the acceleration, as we know, is just change in velocity by change in time. That's the formula of acceleration. So you can apply derivatives to make it dv by dt. And we know that the velocity function with respect to time is negative cosine of t. And then you divide it by dt. And so this becomes negative times negative sine of t, which you will learn. And this is sine of t. So therefore, we see that our acceleration function must be of the form sine of t. Okay? So if the acceleration function is of the form sine of t, then all we have to do is look at this graph and see which function resembles sine of theta. And we find that graph t represents this function sine of theta. Okay? So you just have to sort of get an eye for these things. I would say, so the first function clearly shows cosine of theta. Okay, so this function is of the form of cosine. The function c, you're reflecting function a on the x-axis. So this is of the form of negative cosine. Okay, so so just look at the unit circle. And this function b is also sort of like the form of negative cosine, right? So you just take this cosine function and then you reflect it, okay? So the only function possible with the sine way is d, right? So yeah, we have looked at two different ways of doing it. Just find which one you like the best and, practice it that way, right? Okay, so now let's look at question 3 over here. So in question 3, which one of the following graphs show the displacement x of speed v? Which of the following graphs shows variation with displacement x of speed v of a particle performing simple harmonic motion, right? So in this case, the way we can see is that, so what we're seeing over here is that we want to find how the displacement is changing with the velocity, right? So once again, we simply visualize a simple pendulum and we draw all of those things over here. So this is a simple pendulum. Okay. Now, what we have seen is that this is our positive amplitude, negative amplitude, and then this is our equilibrium. So we can see over here that at the maximum amplitude, you have the maximum displacement. At the minimum amplitude, you have the minimum displacement, right? And you also see that at the minimum amplitude, you have the maximum acceleration. So this follows that acceleration is proportional to negative x. And then at your positive amplitude, you have your minimum acceleration. And we have seen that at our negative amplitude, the velocity is 0, or the absolute value of the velocity is 0. At our positive amplitude, the velocity is 0. And we see that at our equilibrium position, the velocity is going to be maximum, or the absolute value of the velocity will be maximum. Okay, so once we have looked at all of these things, we just tick off points on the graph. So we know that the velocity should be maximum, or the magnitude of the velocity must either be a maximum or it must be, so the magnitude of the velocity must be maximum at the equilibrium. Okay, so maximum magnitude. So just observe that I'm not specifying direction, because if it's going to the left, the velocity will be negative. If it's going to the right, the velocity will be positive. So you're just scared. You just care about the magnitude in this case. So what you will see is that option B is a straight up no, because the velocity is 0, and that's not the case. Option C is also a straight up no, because the velocity should always be maximum at the equilibrium, or the magnitude of that velocity. So now you get to A and D, right? Now at A and D, what you're going to be seeing at A and D over here, right, is that in both of these cases, the magnitude of the velocity is maximum, right, at the equilibrium. But in this case, the other thing you have to note is that the displacement, right, you would have the maximum x in the positive amplitude, and then you would have the minimum x in the negative amplitude. And that's precisely what you see over here. Okay? Whereas in this case, if we take this to be the positive amplitude, you actually have a negative value for displacement, right? Oh, sorry. Essentially, if we see over here, so once again for part A, the velocity, if you look at it, then at your equilibrium, which is at x is equal to 0, the velocity is maximum. That's how A works, right? But then the problem happens that, when you go to this maximum value of x, right, then the velocity is negative. Okay? And that should not happen, because we have seen over here that when you reach the maximum value of x, the absolute velocity becomes 0, because you are at because in this case, you're going to be at your amplitude positions. So when you have max x, the velocity must be 0. So this does not work. And when you have min x, you're at the negative amplitude. That's where min x happens. But at min x, or at negative amplitude, the velocity must be 0, but that's not the case over here. Okay? So if you look at all of those things, if you take all of those points into consideration, the answer comes out to be D. Okay? So once again, you need to visualize the simple pendulum or the mass spring system, whichever ones you like best. Okay, so that's question 3. Now let's look at question 4 over here, okay? And let's see how to go about it, right? So in this case, a particle is performing simple harmonic oscillations, and so which of the following quantities will be unaffected by a reduction in the amplitude? So once again, we go back to our simple pendulum, which has been helping us so much so far. Okay? So, okay, let us just create this like this. Oops. 1 second. So yeah, once again, you just have to visualize this simple pendulum. So we make this image over here. So what we can see over here is that at your maximum amplitude, this is your maximum amplitude, right? Your maximum amplitude plus A. So as we can see that as at our maximum amplitude, the height is going to be the highest, right? So if we are increasing the amplitude, we are actually increasing the maximum height. So for example, this can be one case where you have a very high amplitude, right? So when you have a very high amplitude, this height is very high. But let's say if you make the amplitude a lot lower, like this. So this is a lower amplitude, which means that the height is much lower, right? So if the amplitude goes higher, the height goes higher. And if the height goes higher, then the gravitational potential energy goes higher. And we know that our total energy is the gravitational potential energy plus our kinetic energy. So if the gravitational potential energy goes higher, then the total energy goes higher. Okay? So that's precisely why increasing the amplitude will actually increase the total energy. And so that's why we can't take option A to be our answer, because we want to find which of the quantities are unaffected. Okay? So option A is not the answer. Then option B is also not the answer. This is actually related to option A. So what's going to happen is that as our gravitational potential energy rises, it's going to be maximum at our amplitudes, right? That's when the gravitational potential energy is the highest. And then as you go towards the equilibrium position, all that gravitational potential energy gets converted to kinetic energy, which is 1/2 mv square, which means that the maximum speed will rise because you have more energy to convert into kinetic energy. So therefore, the kinetic energy is not a good answer as well. Okay? Now, the other one is the idea of this maximum acceleration. So for this one, the way you can think about it is that we know that the work done is force times displacement, right? Which is also energy. And we know that the force is mass times acceleration multiplied by displacement, which is the energy. Okay? So that's why, as you can see, if your total energy is going to go higher, then your acceleration will also go higher. Okay? So the energy is proportional to the acceleration in this case. So therefore, even the maximum acceleration is not your answer, right? And the other way you can think about it is that as you keep increasing the amplitude, you keep increasing theta. So in this case, when we're dealing with the simple pendulum, we can see that as theta rises, or as amplitude rises, theta is going to rise, okay? The main thing to note over here is that this is only for values of theta from 0 to 90. Okay, we don't consider points where we go above 90 degrees. So for example, if this is a simple pendulum, then this would be some sort of angle where theta is greater than 90, and we don't consider that. Okay? So as we have seen, if the amplitude goes higher, theta goes higher, and then we know that the acceleration in a simple pendulum is negative g sine of theta. So it's sort of like, if theta is going higher, then sine of theta is going higher. And this sort of relates to acceleration, when acceleration will go higher. I would not recommend this method, right? I think the other explanation where work is force times displacement, this seems simpler. But if you like that method, then that's good as well, right? That just requires a little more complex stuff. Okay, now the last thing is what we learned in simple harmonic motion in the lecture videos is that the period, so the period will be the correct answer. The period is independent of the amplitude. Okay? The period is going to be independent of the amplitude. And the reason is because, if you increase the amplitude, you're going to be increasing the displacement, right? And we know that the time period is time t. But what we're saying over here is that, as you can see, when we increased the amplitude, we also increased the maximum speed, as we saw. So if the displacement goes higher, the speed is also going higher. So we know that time is, in this case, displacement by velocity. So if the displacement is higher, or if the amplitude is higher, the velocity will compensate for it. So the time period will still remain the same. So the period is independent of the amplitude. So answer D is correct, which is this. Okay. Now let's look at question 5 over here. So a body undergoes one oscillation of simple harmonic motion. So what is correct for the direction of acceleration of the body and the direction of its velocity? So they're asking us, how does the velocity and acceleration of this body change? So once again we look at our good friend, the simple pendulum. Okay, so I will just I will erase this over here to get some space, right? And if you want to copy this, you can just rewind back and copy all this. Okay, so now let's look at, okay, just 1 second. Right, so we're going to just use this diagram again. Right, so as we have seen for this simple pendulum, so as you have seen, when you're at your maximum amplitudes, your displacement is maximum, your acceleration is minimum, and your velocity is 0, right? When you're at your equilibrium, the velocity is maximum, but then the displacement is 0 and the acceleration is 0. When you're at your negative amplitude, your x direction is minimum, but your acceleration is maximum and the velocity is 0, right? So they're asking us that how does the acceleration and velocity relate with this? Okay, so the main idea to see over here is that you would draw the simple pendulum like this, right? So if you see, over here, this is what you're seeing, right? So if the pendulum is going to the right, we know that in this case, we know that its velocity is falling, correct? Because at the center, the velocity is maximum. So the velocity is maximum at the equilibrium, but then as the pendulum goes to the right, the velocity falls. And the reason is because the height is increasing, so then the kinetic energy is getting converted to gravitational potential energy. Okay? So as the velocity falls over here, we also see that the acceleration is falling. Correct? Okay? So as the magnitude of velocity is falling, we're seeing that the acceleration is falling, because at our maximum amplitude, we find that at the maximum amplitude, right, the acceleration is going to be minimum. Okay, so at our maximum amplitude, the acceleration is going to be minimum, right? And actually, just a second, this should be B. Okay, so in this case, at our maximum amplitude, the acceleration is minimum, right? Okay. Actually, I think a good way to think about it is if we draw it another way, right? So let's say we have a simple pendulum again, okay? But in this case, we are going to just draw it from these extreme positions, right? So as you can see over here, right, what's happening is that we can see that at the negative amplitude, we have our maximum acceleration, which is just positive g sine theta, right? And then our displacement is minimum, so this is minimum displacement, right? And we know that at our amplitude, the velocity is 0, okay? Now, what's happening is that as the pendulum goes to the right, we can see that because the pendulum is going to the right, the velocity is rising, okay? The velocity is rising as the pendulum goes to the right, and in this case, the velocity is positive, okay? So if the displacement is if the displacement x is in the positive x direction, then the velocity will be positive, okay? Because velocity is just displacement by time. All right? So when the pendulum is going to the right, the velocity is going to be positive, right? And what we find over here is that the acceleration in this case, right, then the acceleration in this case is also positive, okay? Because you have a positive velocity, and the object is going towards the right, so you can say that the acceleration will also be positive, right? And we have already seen that at the left amplitude, you have your maximum acceleration, okay? Now, after this, what happens is that in this case, you get to the equilibrium and you see that the velocity is going to turn 0. The velocity is going to be maximum, right? So the velocity turns maximum at the pendulum at the equilibrium position, but as we have seen before, the acceleration turns 0 at the equilibrium because the acceleration is just negative g sine of theta, and when you're at your equilibrium, the acceleration is negative g sine of 0. So therefore, the acceleration is 0. Okay? So that's why now when the pendulum is going from here to here, the velocity is still positive, right? The velocity is still positive, but the acceleration starts to become negative. Okay? So let us see it this way. What we are seeing is that in this first period, in this first subpart, the velocity is rising because you're going in the positive x direction. The acceleration is also positive. Okay? And then once you go to the equilibrium, the acceleration becomes 0 because the acceleration is falling. So the acceleration becomes 0, but the velocity becomes maximum. Right? But in the second part, the velocity is still positive because the pendulum is going to the right, and if the displacement is positive, the velocity is positive, right? But what we can see is that the acceleration starts to get negative in this region. All right? The acceleration will start to be negative in that given region. Okay? And that's because we have seen that in this case, we know that the acceleration is negative g sine of theta, and we see that when we enter this purple region, theta becomes positive. So, and then in this red region, theta was negative. So, in the red region, the acceleration was negative g sine of negative theta, and then this would just become positive g sine of theta. But then when you enter the purple region, in this case, the acceleration, so in this case, when you enter the purple region, the acceleration becomes negative g sine of positive theta, and so the acceleration becomes negative in the purple region. Okay? So that is the main idea over here. So, so that's why what we can see is that when we look at the red region, so at the red region, the acceleration is positive, velocity is positive, so it's same direction. But then at the purple region, the acceleration starts to get negative, the velocity still stays positive, so it's opposite, okay? But as you see over here, we want to find one oscillation, so we have to do one entire period. So we have to analyze a little more, okay? So now if we look at one entire oscillation over here, we said that our release point will be at our negative amplitude. So we analyzed this line. Now we have to analyze it going back, okay? So now what we'll do is that we'll say the pendulum is going back. So therefore this is the starting point of the pendulum now. So it goes up here and now it's going back. So as the pendulum goes back, we see that the velocity turns negative because you're going in the negative x direction. So this is x, y, negative x. So because the pendulum is going to the left, it's going in the negative x direction. And so because of that, your velocity is going to be negative. Okay? And in this case, what we start to find is that the acceleration is also negative in this region. Okay? The reason the acceleration is negative in this region is because, once again, theta is positive. The acceleration is negative g sine of theta. And, because theta is positive, the acceleration gets a negative sign. So in this green region, the acceleration is negative and the velocity is negative, so it's in the same direction. Okay? Now after this, you're going backwards over here. So when you go back in this direction, what you're going to be seeing is that, let's take purple, or a light purple this time. So when the acceleration, when the pendulum is going back to its starting position, what we can see is that the acceleration turns positive because you've got negative theta over here. So we know that the acceleration is negative g sine of theta, and because theta is negative, this is negative g sine of negative theta, which is positive g sine theta, right? So the acceleration becomes positive, but the velocity is negative because you're going in the negative x direction when you're going towards the left, okay? So therefore, in the purple region, the acceleration is positive, but then the velocity is negative, so this is opposite. So this is the entire thing for one oscillation, okay, for one entire period. So if we color code this, then it becomes like this. So in this case, the red section is going this way, the purple section is going this way, the green section goes back, and then the light purple section goes back. So this is how we are looking at one oscillation or one period. And so we can see that in one oscillation, 2 times they're in the same direction, and then 2 times they're the opposite direction. So, in this case, what we can see is that the acceleration and the velocity are in this case, they're opposite for half a period. Okay, so the answer will be B. Opposite for half a period. All right. Okay, so this is part 1 of the MCQs, and then we'll solve a few more questions in the other parts, and see you then. Okay.